Hello, hi. My name is Wilfred Zagre, and today I will be doing a presentation for my thermodynamic class. And today my presentation is gonna be focused on a refrigerant, uh, and my refrigerant that I actually chose is the refrigerant R407C, which is actually a blend of hydrocarbon. Those hydrocarbon are difluoromethane, pentafluoroethane, and 1112 tetrafluoromethane. So it's the whole blend that actually constitute the refrigerant R407C. So basically, studying this refrigerant is very interesting because refrigerants are a thermodynamic process where the fluid actually absorb the thermal energy from uh, from the very low temperature surrounding, and at the same time eject that same thermal energy, but at a very higher temperature in the same surrounding. So it's very interesting how this process works because they actually take the energy at a low temperature in one surrounding and then give again the same thermal energy at another surrounding, but at a very higher temperature. So, okay, we're gonna talk about this process and also discuss how the whole thing actually works. And as I was saying, the refrigerant actually is constituted with four parts. It has four major components, and those components are the condenser, the compressor, the evaporator, and the expansion valve. And I have this sketch right here that I did to actually help me explain you guys how the whole process works. And this sketch is basically the same sketch for every refrigerant that we have in our book, but as they actually function differently. So in this sketch, basically, it's going to explain us how the liquid is moving from one point to another point with all the chemical reaction that's going on in there that's actually constituting the refrigerant function. Because like I already said, it goes from we have something being transferred, being absorbed at a lower temperature, and then being redispensed at a higher temperature. So we already know it's going to be heat exchange and a couple of other chemical reaction. So basically, I'm gonna start explaining this sketch, and I wanted to point that I also have the pH diagram over here, and the pH diagram have like actually two phases, which is the pressure and the entropy. The pressure is what going up, and the entropy is what going from right to left. And it's sort of like if we could have moved this diagram to over here to this sketch where I have the condenser, compressor, evaporator, and the valve, because it kind of like also have the four phases that I have over here. But anyway, I'm gonna go deeply into it and explain. So I'm gonna start by point four. Point four is right here. It's where actually, I mean, I wouldn't say that's where the cycle starts because it's a cycle, a repetitive cycle. So it sort of doesn't have a end or beginning, but I can call uh, stage four sort of like the initial start, because over here we have the two phase liquid. Well, the two phase component, we have a liquid and vapor at point four, and that liquid and vapor is actually going to move into the evaporator, and the evaporator is just his job is actually to change this substance to another substance. So in the evaporator, it's gonna the liquid and vapor is gonna receive heat. That's why I actually mark the Q over here. Heat entering over here. So we're noticing the pressure is constant. It's just the entropy is changing because we're on the entropy line going toward the right. So enter the evaporator and you receive heat. And once it's actually leaving the evaporator, we're actually noticing that it's going to change to a saturated vapor. And this saturated vapor is the product from leaving the evaporator. So we are point A now. From point A, like I was saying, temperature, the pressure is constant, so it's an isobaric process. I have over here delta P equals 0. And from the point one now is going to go in the compressor. When you go into the compressor, you guys can notice that now the pressure is going to change. So the pressure get higher in the compressor, and the saturated vapor get compressed, and it's going to turn to a saturated gas. So over here we are point two, where we have a saturated gas. Then this saturated gas actually redirected now to the condenser, and in the condenser, the saturated gas is going to get condensed. So by getting condensed, it's going to lose temperature. It's going to lose heat. So the temperature is going to lower. So the vapor, the gas in there, losing temperature is now going to turn to a liquid. So it's going to turn more precisely to a saturated liquid. So at point 3, right here, we have a saturated liquid. And the saturated liquid is being redirected now to the valve. So from the expansion valve, it passed through the same process where the pressure is decreasing. In the asymptotic process, the pressure is decreasing and it's coming back to point 4. And at point 4 again, we're going to have liquid and vapor. So the cycle continues. So it's not just a one-time thing. The cycle is going to keep repeating itself. And that's how we get the process of the refrigeration process. So by doing this exercise, we were actually given guidelines, low temperature, max temperature that we couldn't pass, and I had to pick my refrigerant according to that. So that was the problem statement, and also we have to work with the so the efficiency is equal to 60%. And so in my calculation, I made sure that those actually given properties in my homework is what coincide with this thing that I actually picked. So basically, and we also have to state some guidelines for this process to be possible. And those guidelines is basically like the assumption that we almost do all the time when we have thermodynamic homework. So I'm going to read some of those guidelines that we have stated. I mean, I'm pretty sure that we're already familiar with it, but I'm still going to read it again. So we actually assume that this is an open system, so there is a total exchange and a significant loss of energy. Also assume that this operates at a steady flow and steady flow pressure. Kinetic and potential energy is very minimal, so we neglect it. And the compressor and the expansion valve devices are adiabatic. Also, the evaporator and the condenser are considered at constant pressure, and the asymptotic efficiency of the compressor is going to be selected at 60%, which is the 60% that I was talking about earlier. So we have to take all these into consideration, and by also using the pH diagram in my presentation, I have a PowerPoint and a word writing that actually explain the pH diagram, which I was telling you earlier. We can actually compare that to this because it's literally the same process. What's going on over here is what's explained in the pH diagram, but with more accurate numbers than this sketch. So these numbers is actually what actually help us to solve this homework and make all these calculations, same as calculating the compressibility factor and all that which we did in our previous class. So we have all these numbers that is in my presentation on the Word program. But also one thing I want to talk about also is the reason why I picked this refrigerant, because the refrigerant R407 is it's a very good refrigerant because not only is good for the environment, I did the research and I found out that it has 0% ozone depletion by using it. And it's very affordable. It costs about between $4 to $7 a pound. So anybody can basically just get it and use it in this process. So like this actually makes it a very efficient refrigerant, which is the reason why I picked it. So by ending up this presentation, I just want to let you know that all the calculation that was made, we came and estimated that the efficiency of this refrigerant can function at 60% without no problem at all. So with that being said, I want to end my conclusion by thanking Dr. McIntyre for giving us all this information that we had on the project, because it was very helpful, and that's what guided me towards being able to accomplish all this work. And also the paper that we actually read by Dr. I'm sorry, I don't remember exactly the name, Al-Faj and Abu Malawi, and that paper was very, very inspiring for me to be able to make this presentation. So without holding that much time, if you have any questions, I will be pleased to answer them. Thank you.